fluids, like any other substance, are made of molecules. Weak cohesive forces keep molecules attracted to each other. However, the molecules are in constant motion. Distance a molecule travel before hitting another is called the mean free path lambda. Its mean free path is directly proportional to the temperature and inversely proportional to the pressure. If we look at a liquid at microscopic length scale, we would be able to see molecules of the liquid moving in the space bouncing off each other in the container wall. At this length scale, fluids are discontinuous spatially. However, we very seldom work at this length scale when handling fluids. At a larger length scale, for instance, when we consider a tiny liquid droplet of about 1 mm radius, it appears as a continuous phase. In this example, the diameter of the droplet is called the characteristic length, the length scale at which we observe the droplet. Assume the characteristic length scale to be L. The ratio between the mean free path and the characteristic length gives a non-dimensional quantity called Knudsen number. Knudsen number gives a feeling about the continuity of a fluid at the length scale of observation. The criteria for this is following. Fluid can be considered as a continuum. Rarefaction effects start to influence the properties. The assumption that a liquid is a continuum starts to break down. We are looking at molecules at a length scale smaller than their mean free path. The continuum approach breaks down completely. The figure you see shows the variation of mass to volume ratio of a fluid across several orders of magnitude and length scale. Consider a minuscule volume V, say a volume with few angstroms in diameter, that can hold few molecules initially. If we increase this V volume in size, across length scales, the number of molecules it can hold increases. Molecules moves in and out of this hypothetical volume element constantly. At the molecular length scale, the rate of molecular movement has an effect on the density, making the value to fluctuate. However, at a rather large length scale, say around not equals 0.001, oscillations start to converge to a constant value. Above this length scale, the fluid can be treated as a continuous medium showing constant bulk properties. It is this approximation that makes us to treat fluids in the way we present in this book.